Okay, so I'm going to assume you are more or less familiar with how to do Bode plots of systems that have real poles. But as you know, the general polynomials can be factored into, of the kind of polynomials that we need, can be factored into real poles, or real roots, and possibly complex conjugate roots. So I'm just going to talk about how to do a particular special case, and as we need it, we'll talk about other special cases. So suppose you had a transfer function h of s that can be written as a constant in the numerator and then s squared plus 1 over q s times some omega naught plus omega naught squared. Or let me rewrite that in my favorite form. This will be a different k here, where we have the normalized version of this. So that's 1 over q times s over omega naught plus 1. And there's a couple of things I want to talk about this function. We're going to do Bode plots of it, but we can do a lot without just jumping into a bunch of rules by just looking at, well, let's look at it another way. As I said when I was talking about the Bode plots for things with a single function, we're looking at two asymptotes. We're looking at the case where s is much less than the frequency, some characteristic frequency, which is omega naught. That produces one region. When the magnitude of s, well, when s equals j omega, this is okay, is much greater than this characteristic frequency, and then we may have something when the magnitude, when s is in the order of magnitude of omega naught. We may have a third region. But the main asymptotes are for the low frequency range up here and the high frequency range here. As we'll see, as you can see by just looking at this, when s is really small, much, much less than omega naught, these two terms are unimportant, and the gain of this thing should be proportional to just k and independent of frequency. All right, so when we make our magnitude Bode plot, we're just going to have the magnitude of h of j omega, s equals j omega. This thing is just going to be k expressed in decimals, right? 20 log of k. And then at some very high frequency, the one is going to, this term is going to dominate. This has got s to the second power. This has s over omega only to the first power. At sufficiently large values of s, these two are unimportant, and this thing is proportional to, at high frequencies, k divided by omega naught over s to the minus 1/2 power, or s to the minus squared power. This is minus 40 dB per decade. So no matter what value we have for q, for example, this thing gives us an asymptotic plot where at low frequencies it's proportional to k, and at high frequencies it goes as minus 40 dB per decade. So this is called a low-pass transfer function because it passes low frequencies, and if we think of it as a filter, it drops out or attenuates the high frequencies. And if I do this right and get this line straight, these two curves would meet at omega equals omega naught. Okay? Now, in another lecture I pointed out, but we can see it by just doing some factoring here, that this thing can be written, if we have real poles, then this thing can be written as k divided by s plus an omega 1 and an s plus omega 2. And we talked about how we can estimate those two things. And the answer was that my two frequencies are approximately, one of them would be omega 1, which for real small values of q, this is omega naught times q, which is much less than omega naught. So this thing is approximately omega naught times q for q much, much less than 1/2. And omega 2, as we'll see, is omega naught divided by q, such that, as you can see if you multiply this out, we've looked at it before, that no matter what q is, that omega 1 times omega 2 has to equal omega naught squared. And you can just multiply this thing out, and you'll find that the constant factor of this thing has to be omega naught. This has got, let me try this again. This will be s over omega 1 plus 1, s over omega 2 plus 1. And again, we can see that when we multiply out the first two terms, the omega 1, omega 2 has to equal omega naught. So if we make this plot for q much, much less than a half, we'll get a second pole out here at omega 2, which is at omega naught divided by q, where q is less than is a small number, so this is the higher frequency. And on our log plot, omega is to omega 1 as omega 2 is to omega naught. So these two distances, if I had done it right, are supposed to be the same on the log scale. All right? And so this is our asymptotic approximation then. It goes from here to here. And then in between these two poles, when we're much greater than the first one, then we break down at minus 20 dB per decade. And it will continue at that slope until it hits the second one, which is omega 2, and then it drops off at minus 40 dB per decade. And notice that this equation comes from this. And so this is our plot. This is what we get. All right? We go flat at k, or the log representation of k, until we get to omega 1. And then we drop at minus 20 dB per decade. All right? We pass through omega naught, and we go just as far over to the other side as we did here, and we get down to the next pole, omega 2, which is omega naught over q, and then from there on we drop at minus 40 dB per decade. Now that's only valid for q much, much less than a half. Remember that if you get close, as these guys come closer together, as we increase q approaching 1/2, these guys get closer together. If you remember, at one point we had that this had to be divided by an f, and this had to be multiplied by a function f, and I'm not even positive I can remember this, but it was some function that was not especially memorable. But this function is basically 1 until these guys get really close together, so that I usually don't even remember the f business, but there it is. And when these things get closer together, we get a family of curves as we keep going up, that these guys start approaching each other, and eventually they meet at a frequency where q equals 1/2. That's the critical damping point where these two things are equal. Now, remember that the approximation when they were widely separated was that we were down by a factor of 3 dB at this frequency, and that we had an error of 3 dB at this frequency. As these two guys get where they meet, we get an error of 3 plus 3, or 6 dB, in the case where q equals 1/2. So that'll be the gain for this case. Now for q greater than 1/2, they go complex conjugate and things begin to change. And it's more convenient to write things in this form as we've talked about. In this case, we talked about the magnitude of the poles and the phase, but let's break this up into our three regions. And the real trick here, when we get to the complex conjugate, this actually turns out to be easy to get what we need. It doesn't look like it's going to be, but it will be. So stick with me. Then for complex conjugate values of this thing, or really for any values, S equals j omega over omega naught quantity squared plus 1 over q times j omega over omega naught plus 1. So this is the same thing we've been doing in every case here. Suppose we evaluate this transfer function for S equal j omega. So what is the gain at the center frequency, right as we go through the transition where our approximations are the worst? Well, this becomes omega naught, this becomes omega naught, this is 1, this is j squared. J squared is minus 1. So I'm evaluating the magnitude of hs at S equals j omega. This becomes minus 1, this becomes plus 1. Those two guys are going to cancel. This one becomes just j, and this thing, actually the whole transfer function, let's go ahead and do that. This transfer function, h of j evaluated where S equals j omega, is k. These two terms cancel. We get times q, and there is a j in the denominator, or a minus j out front if you want to. Now the magnitude of h at that frequency is equal to just q times whatever k was. Now this doesn't depend on whether it doesn't depend on what q is. This is true every time. If we evaluate for any value of omega naught, then the value at this point at s equals omega naught is just q times whatever it was before. These are for q equals much less than a half. So these numbers are much less than a half k on the log scale. When the two are equal, this thing should be 6 dB low or a factor of 2 low because q is equal to a half. And now we can see what happens as we go complex conjugate. These two things now get on top of each other. We get peaking like this. And this thing goes above the pole, above the asymptotes. And if you evaluate this thing at this point, you will find that you are q times higher than that, and that this distance is q expressed in decibels. And so as q gets higher and higher, we just get steeper and steeper, and we just get these curves. So that's what the magnitude response of this low-pass filter is, or low-pass circuit is. For q equals a half, we get two breaks, individual breaks. Eventually they meet for q equals a half, and after that, the values at the center frequency are just following by different values of q, getting peakier and peakier. So you could say that this breaks into three regions: a low-frequency region, a high-frequency region, and a region that's somewhere in between. And you can separately do each one of those and make really remarkably accurate sketches of the magnitude response to this low pass. Now later on we'll talk about other possibilities. Another thing we can do is to look at the phase response. And the phase response, let's do them when they're widely separated. What we expect is we get to about 1/10 of omega 1, and the phase that was at 0 of this transfer function, assuming there's no minus sign out front, we get to 1/10 of omega 1, this thing starts down. If the poles are widely separated, it'll be at minus 45 degrees at omega 1. This is 0.1 omega 1, and this is 10 times omega 1. And now it'll just be sitting there, and then symmetrically on the other side, when we get to 1/10 below this guy, it'll start down some more, and eventually, when it hits this guy, it'll be at minus 45 plus 90, that's minus 135 degrees, and at 10 times omega 2, so this is at omega 2, is where it's at minus omega 5, and eventually it hits minus 180. In the middle, has a flat region at 90 degrees. Okay? And so that is what we have with widely separated poles, which is the case for q much less than a half, like we showed in the magnitude response. Now, as q gets larger, these two things come together trying to approach omega naught, which again is just the geometric mean of the two. And eventually they will meet each other and begin to overlap. So when we get to q equals a half, we get to a thing where this thing at a 1/10 of omega naught, actually, they're going to all be equal to omega naught. So at that point, this thing will start down at 1/10. It will come through like this, and it'll meet minus 90. It'll be at minus 90. So this point is always at minus 90. A few minutes ago, I just said that h of j omega naught is equal to kq divided by j. Minus j is minus 90 degrees. So it's always that. And in this example with q equals a half, these guys are at omega naught over 10 and omega naught times 10. So what we see now is that we get a single straight line. This thing is 90 degrees per decade. As we begin to increase q, we get a family of curves where these things get steeper. So when q is equal to, say, 1, this guy ends up having a slope that's twice as great as it did when q was equal to 1/2. And so the slope of this stuff is proportional to q. The slope is proportional to q. And so it just gets steeper for increasing q. And we get this family of curves. If you're ever measuring a thing and you know that it's complex conjugate and you want to know what is the omega naught of the thing, find the minus 90 degree point, because that's invariant. Just a little tip. But you got to make sure there's no other poles and zeros in the system. Okay, well that's enough about this. Later we'll talk about other games we can play with the magnitude and phase of complex conjugate roots. We'll talk about that later.